organized by the Communication Society WTC Special Interest Group on RSMA. So this is our third webinar series in this year, and it's great honor to have Professor Christos Masouros from University College London, UK, as our distinguished guest speaker. So let me briefly give introduction of Professor Masouros. So he is a professor of the Signal Processing and Wireless Communication in Information and Communication Engineering Research Group, Department of Electrical and Electronic Engineering, and affiliate with the Institute for Communication for Connected System and UCL. So he has several awards, including IEEE SPS Young Author Best Paper Award and Globecom and WCNC Best Paper Award and several exemplary editor and exemplary reviewer on IEEE journal. And he is the editor for Transactional Wireless Communication and Open Journal of the Signal Processing and editor at large for Open Journal of the Communication Society. So he has been an editor for IEEE TCOM and Communication Letter and guest editor for a number of IEEE JSTSP and JSEC issues, special issue. So he is a founding member and vice chair of the IEEE Emerging Technology Initiative on Integrated Sensing and Communication and vice chair of the IEEE Special Interest Group on Integrated Sensing and Communications and chair of the IEEE Green Communication and Computing Technical Committee and Special Interest Group on Green Integrated Sensing and Communications. So before the talk, so let me remind you the rule of this talk. So during this 15 minutes talk, audience should be muted but you can type your question during the talk in the chat box. And so after the talk, we will have the Q&A session, the 10 minutes Q&A session, and yeah, audience can unmute it and raise some questions. And otherwise, I can pick some question from the chat box. And yeah, that's all for our rule. So enjoy the talk. So let me share the screen and. Yeah, so please, so share your screen and start your presentation, Professor Masouros, if you're ready.
I'm hoping that you can see this.
Yeah, perfect.
Pick up my pointer. Let me minimize the window here. Okay, I think we're ready. So yeah, once again, thank you very much for your kind invitation. I hope I can share with you some insights on some problems that I think are important for RSMA, rate splitting. This work has been done with the lead of Abdelhamid Salim and Aryan Koshik in my team, and together with Onur Dizdar and Bruno Clerks in Imperial College London. So as I said, I'd like to cover some important aspects, or at least some interesting aspects, I think, on security, and some practical aspects on rate splitting multiple access. And I'll discuss about the application of rate splitting on ISAC, on integrated sensing and communications, as an emerging application. So, I mean, I don't think I need to spend too much time on this. You've had already a season of RSMA, just so that we're at the same page. So we're discussing a downlink scenario where one base station is communicating to K single antenna users. Now, rate splitting is all about splitting the signal that the base station transmits into a common part, and the common part can be either one user's signal made common for everybody, or a combination of all user signals forming the common part, and then private parts to each user. So that means there's K+1 streams for K users. Now, all users, and this is how it's done, right? So you have the common and the private parts pre-coded and allocated their portions of power from the power budget in the base station. And then what the receiver does once receiving the signal is, first of all, it will decode and cancel the common signal. So we'll decode the common signal, reapply the channel effects and cancel that from the received signal. And then the private part of its own message, it will decode, treating everything else that remains as noise. And by allocating different powers or designing your precoders in the more general case, you can basically split between the common signal and the private signal. And that has been showed already many times. That is, it provides the uniqueness is that it provides a flexible trade-off between treating everything as noise or decoding and canceling everything. And this trade-off is very useful in a number of scenarios. And at least to my observation, most useful in cases where we have imperfect CSIT, where we can break this kind of ceiling in the sum rate by treating some of the signal as noise and some of it decoding. Now, one important challenge is to do with practicality. And I think this is quite often neglected somehow in the RSMA literature. So there's definitely scope and a lot of motivation in applying RSMA in the case that you don't have perfect channel state information at the transmitter, but often people ignore the effects of imperfect channel state information at the receiver. And that's one thing. Now, I forgot to say, the most important thing is this successive interference cancellation on its own. Very often it's assumed as perfect, but in practice, I'm not sure, how perfect that would be. So first of all, that first introduces extra complexity, and this complexity involves a symbol by symbol cancellation. And if you take a classical, let's say LTE frame, symbol time is less than a millisecond. So that has to happen on a less than a millisecond basis, symbol by symbol. Or even if you process a whole block at once, still that will take a lot of complexity in a block. So complexity is one thing. The second thing, as I mentioned, is whether or not you can actually cancel things perfectly, right? So as I said, at the receiver, you will estimate the common signal, but you will also need to have estimates of the channel of the precoder or their composite matrix, right? And this is typical for all kinds of precoding approaches. Now, often this is neglected, and we often assume that once I can guarantee a certain rate for the common signal, I can perfectly remove it. But that's a rather idealistic approach. It typically assumes long codes and so on. So aside of the complexity, this further entails, first of all, you need to estimate the channel at the receiver, and you need to use that to reconstruct the interference here that you see from the common signal. By estimating, this is extra complexity, the pilot signals and so on, the CSI estimation is an extra bit of effort that the receiver has to do. It also is subject to errors on its own. So H, the estimation itself, will introduce errors in the knowledge of the channel matrix, which we model by H here. And even if, let's say, the base station, who has to feed back in most cases, or feed to the users the channel or the precoding it uses for the users to be able to cancel this out, or the composite matrix, that's subject to quantization, right? You're going to use a given number of bits to convey that. So that will introduce quantization errors or noise in communicating this information. So it's very difficult to get the CSI at the receiver right? So very often it's going to be imperfect. And that means also the successive interference cancellation at the receiver is also going to be imperfect. And this is not just a thing for rate splitting. It's also for NOMA, non-orthogonal multiple access, which has been shown to be let's say, a subfamily of techniques of RSMA. And here's an example where we have the user pairing NOMA approach. So we have two users, so the received signal is the sum of two users. And typically at least one user, so let's say user one, the strong user will have to decode the signal of user two and remove that. and then decode its own signal. So that again is excessive interference cancellation. It involves errors. It involves channel estimation at the receiver. It involves extra complexity on a symbol by symbol level, right? And I'll hope to show a technique that improves this situation on this context of NOMA. Now, the other important challenge, I think, for RSMA is that of privacy and security. So as I said, part of the user signals is going to go to the common signal, and that common signal will be decoded by everyone, all the users. So that means that part of my signal, if I'm user 1, is going to be decoded by user 2. And now there are scenarios where you want to have my information private, for even if the other users are legitimate users of the network, you want to ensure some privacy, right? And you know, revealing this through the common signal, you know, jeopardizes this privacy. So another user of the network could potentially eavesdrop my signal, and that harms my security performance. So here I have the example of the common signal being the single user 1. So user 1. So as I said, the common part is visible to everyone. The private part is what you have for your own. So user 1 will receive its own signal. That's fine. But user 2 may receive the common signal of user 1, and user K the same. So each user has the opportunity potentially to eavesdrop the information intended for the other users. And I think that's an interesting challenge and an interesting scenario. It's not the typical security scenario where you have like eavesdroppers being, you know, outside the legitimate space of the network. It's now the legitimate users that, you know, you open up the opportunity to all of them to eavesdrop each other's channel. And there's many applications, emerging ones, like offloading computation or healthcare applications or IoT applications where you really want to ensure privacy. And again, I think it's very interesting, at least from an academic perspective, to study the trade-offs between, you know, having this common signal, having a lot of signal in common, and, you know, the gains that gives you for in terms of the rate, the trade-off against revealing part of the signal and reducing, let's say, the security of the signal. So with that motivation done, this is what I'll try to cover in my talk. So first of all, I'll discuss some recent work we did on you know, making RSMA secure and looking at trade-offs in security in rate splitting multiple access. Then I'll talk about another research technique from my group on solving this issue of symbol by symbol successive interference cancellation. And I'll finish off by discussing the gains and an RSMA design for the emerging topic of integrated sensing and communications. So first, this privacy and security issue. So as I said, we have the signal that the base station transmits. We can tune how much of that is common and how much is private, and these is typically done through the power budgets of the common signal and the private signal. This is the total power budget that the base station has at its disposal. And we have 1 minus t of times that will be what I allocate to the common signal. T times that divided by the number of users will be how much I dedicate to the private signal. And that's the budget for all K users. Now, it's obvious that when I have all my signal being common signal, there's no secrecy, right? Everybody knows all the common signal, everybody else's signal. As I said, there's many variations of RSMA. The common signal could have just one user's signal or a combination of everyone's signal. But in every case, whatever is in the common signal, if all my signal is common, everybody will know that. So there's no secrecy. And then the other extreme case is the maximum privacy, where I have this splitting factor equal to 1, where all the signal is private, and that's the conventional, let's say, pre-coding approach. And here are the SNRs for the common and private. Maybe I'll go very quickly through those. So if HK is the channel of the kth user, WC is the pre-coding for the common part. And as I said, this is the power budget of the common part. This is the useful signal in terms of decoding the common signal. and everything else, the private signals act as interference. And then you have a noise, and this is the SNR. And then the SNR for the private signal of the kth user will be that user's signal pre-coded by its dedicated precoder over the interference from the other users, assuming the common signal is perfectly cancelled out. And then you have the rates of the common signal and the private signal. And this is all classical RSMA. Now, as I said, having this common signal opens up the opportunity to the legitimate users to eavesdrop each other's signal. So we want to quantify what that means in terms of secrecy rate. So here we have the common signal rate, the private signal rate, and then what do we have here? So this is the rate, the total rate in terms of the sum rate of the users with RSMA. So we'll have the common signal, and the common signal has to be encoded with a certain rate that can be achieved by all the users, and that's why we have the minimum here. So we'll have to satisfy a minimum value that everybody can support, all the users. And then this is the sum rate of the private signals of all the other users. E is for expectation. Now, the secrecy rate we define as this is the rate for the user of interest, let's say, so the common signal plus the kth user's private signal. And then the eavesdropping rate is going to be the common signal, which is, as I said, open to everyone, plus whatever another user, the ith user, can eavesdrop from the kth user's signal. And it turns out that RC cancels out, and the secrecy rate is this expression over here. Again, this rate is a function of the SNR, and the SNR is a function of the power split, okay, in this case. And again, you can see here from the math that when T, this splitting factor is 0, you have a 0 secrecy rate, so there's no secrecy. When T is 1, you have the highest privacy among the users. So you can take this into account in the design of the power allocation. So we took this power allocation approach. So as I said, the interesting trade-off here is the splitting of the signal. So if I split the signal too much common signal, I will have, or a lot of common signal will give me perhaps a lot of gains in the sum rate, but it will jeopardize security a lot. If I split very little common signal and most private, I'll have a good security performance, but at the expense of perhaps a reduced sum rate. So what we want to do here is optimize the split in terms of this factor T over here, the power budget split, such that we maximize the secrecy rate, but we maximize the sum rate with rate splitting, subject to a secrecy rate threshold, and subject to the power constraints. And you can probably solve this by complex math, but Abdel here, our first author in this paper, first of all, he did some great work in characterizing this performance analysis of the sum rates. So the RSMA sum rate and the secrecy rate for two cases. First case is when you use maximum ratio transmission for the common signal and zero forcing from a private, and it turns out that the secrecy threshold has this function over here, and you have all these notations here that I'm not going to go into detail. And the second case is where you have maximum ratio transmission for the common signal and MMSC for the private signals. Again, another expression of the threshold over here. And using those, he designed a heuristic approach to find the optimum power split, which involves a first step where we look at the secrecy rate, and you can see that the secrecy rate is an strictly increasing function of the split. As I said, no secrecy at T equals 0, highest secrecy at T equals 1. So if you have a threshold for the secrecy rate, let's say 1.5, from that you can actually get the threshold for the splitting factor. And this is the expression of it for zero forcing and MMSC. And then having determined that, all you need to do is optimize T within the allowed values that will already satisfy this secrecy rate. So then if we go into the sum rate, I can now optimize T within the values from TS, which was determined in terms of secrecy, all the way to 1, right? And with this very simple heuristic approach, low complexity approach, he's able now to design this power splitting approach. And only a couple of indicative results in this case. So this is a result for 5 base station antennas and 5 users. We have an SNR of 5 dB, and we have 2 cases, one for the zero forcing and one for the MMSC. And we also have imperfect CSI at the transmitter. Here we referring to the previous stuff I mentioned about imperfect SIC, here we also employ the assumption of a perfect successive interference cancellation at the receiver. I'll deal with that in the later part of the presentation. So for zero forcing, we use this threshold, secrecy rate, and for MMSC, we use 0.72. Now, here are the secrecy rates. So the blue is for zero forcing, the red is for MMSC, and by looking at the target secrecy rate, so it was 0.41, that will give you a threshold value for T. Same here, this value over here will give you a threshold value for T, another one. And then you go to the sum rate and you check for the optimal value in this interval for zero forcing, in this interval for MMSC. And it turns out that in these cases, these are the optimum values for secure rate splitting. So the key observation is here I have, without taking into account security, for a security agnostic rate splitting approach, this would be my optimal power splitting, and this would be my optimal sum rate. Now, once I've taken into account the security, I have a different value and a slight sacrifice of the sum rate of the users in both scenarios, in MMSC and zero forcing. So there's an interesting trade-off where you sacrifice some of the rate gains for rate splitting, to ensure a certain threshold of security. Of course, you can do many variations of that. Perhaps you could have weighted optimizations of secrecy rate or any other kind of variation. You can also optimize the precoders directly, and I think Bruno has some work on that as well. And here we have a couple of more results for the power splitting approach. And here we have the direct trade-off between the sum rate and the secrecy rate. And here you have this kind of concave shape, let's say, and here we have increasing SNRs. Now the observation here is, so first, when my secrecy rate region is, my secrecy rate threshold is low, you get an increase of both sum rate and secrecy rate, because essentially I don't need to consider the secrecy rate because it's too relaxed. Then once the secrecy rate constraint becomes important and active, then we go into this trade-off region, where if I want to further increase the secrecy rate, I have to sacrifice the sum rate, and vice versa. If I want to get a higher sum rate, this will be at the expense of reduced secrecy. And this is the same for both scenario zero forcing and MMSC. And there's quite a few other results, and as I said, a lot of theory that Abdel derived in this paper, and I'd be happy to recommend you to have a look at this paper. So that was it in terms of the security aspect. Now, the next thing I'd like to discuss was, remember, I talked about this practicality of having the symbol by symbol successive interference cancellation. So next, I'm going to discuss, an approach to this, to basically removing SIC through the concept of interference exploitation, and that's something that my team has been working for a while on. So again, just to briefly reiterate what the problem is here. So I'm going to focus on this NOMA approach, and in particular the user pairing, but some of this is applicable to general RSMA or a number of RSMA techniques and scenarios. So here we focused on the simplest, let's say, scenario on a NOMA where you have spatial separation of the users and you just pair couples of users, and you apply NOMA on these pairs of users. In the more general approach, I should emphasize, here we have only one successive interference cancellation for one user. In the more general NOMA approach, you can have n stages of cancellation, and that's even more complex, even more estimation, even more things that can go wrong, even more estimation of bits and data, and also channels, right? But we'll take the least complex approach to demonstrate this. So in this case, we have, as I said, the base station encodes both user signals in the same spatial resource. And the received signal here is going to be the sum of the two signals for every user. And now the user one will have to first decode or estimate user's two signals. So if this is the received signal of user one, we have the signal of user two, that's the interference from the signal of user two, the signal of user one plus noise. Now for interference cancellation, I will need to estimate user's two signal in the presence of X1, also estimate the channel, estimate the precoder, or have it fed to me by the base station. And then I use that to recreate the interference, an estimate of it, or an approximation of the interference, and subtract. In the perfect case, these two guys will go away and I have a single user performance. But in practical cases, there's many things that can go wrong. So you can, even if you had, for example, let's say a perfect channel estimate and a perfect precoder estimate, even if you get the detection of symbol 2 wrong, you can perhaps up to double this interference, right? If it's BPSK, I'm actually adding, if I get X2 wrong, a 1 instead of a -1, I'm actually doubling interference here. So I'm making things even worse for for my receiver. So many things that can go wrong here. As I said, the extra complexity of estimating things, the extra complexity of subtracting and recreating and multiplying and so on. And then user 2 will just decode its own signal in the presence of user 1 interference. So what's the solution to this? As I said, I'll show you an approach based on exploiting interference. And this is something that we've been working on in my team for a while. So the approach is basically looking at the modulation level of the constellations. And here are some basic PSK ones. You can apply the same for more general constellations. So what is constructive destructive interference? So if we take BPSK, this is the decision threshold, the 0 axis. Anything that pushes my signal away from the decision threshold is constructive. It contributes to essentially to the signal to noise ratio of my receiver. Anything that pushes it towards the decision threshold is destructive interference. So it hinders my detection of my symbol. So the green dots are constructive, the red dots are destructive, and you can apply this to higher order modulations. Here you have 2 decision thresholds. So your green area, the constructive area, is going to be smaller, 8 PSK, and so on. We've been working on these since about 2006. Some early works were on CDMA systems, earlier then works on MIMO systems, some closed form techniques, some optimization-based techniques. And in classical basic downlink scenarios without rate splitting, we've been showing a lot of orders of magnitude reduction in transmit power by exploiting this energy of interfering signal of constructive interference. So orders of magnitude power reduction to achieve a certain symbol error rate. Now, a key benefit that we're going to use here for this NOMA example is the fact that you don't need to cancel things at the receiver if you apply this constructive interference precoding. So here's what you get with conventional optimization-based beamforming. So optimization-based beamforming, you get your channel estimates at the transmitter. You optimize a certain optimization, let's say maximize signal to noise subject to power constraints. It's a classical optimization. You get your precoders, and then at the receiver, first thing you need to do is you need to equalize your signal. So your signal will be multiplied. So you have the product of the precoder with the channel. The receiver needs to know that to be able to equalize the signal and then detect. So Q here is the detection function of my signal. And that means I need to have an estimate. So I either estimate the channel and somehow optimize the precoder at the receiver and hope to get the same precoder, or I need to have my base station feed forward, if not the channel and the precoder separately, at least this composite factor over here, right? And again, that's subject to an increased complexity, subject to errors, subject to quantization, and so on. Now, by exploiting this interference exploitation, as I said, you allow interference that pushes me away from the decision thresholds, and this is an example for QPSK. So now all my received signals for the user of interest will lie in the constructive area of the constellation, and that means there's nothing I need to equalize. If I just use this symbol and apply detection, so QPSK detection, I'll get the right response, right? So nothing here to equalize in terms of the channel or anything. I can directly estimate my signal. So the benefits here include reduced complexity, no SIC, or no equalization in this case, no need for CSI for training, for collecting CSI at the receiver, no effects of CSI errors or quantization errors, and so on. And we've shown those in a number of works in this area. Perhaps the best place to read about symbol level precoding or constructive interference is this overview paper, if you're interested. Now, how do we want to apply this to this NOMA case? So here's the classical NOMA again. So I'm again repeating here the cancellation. Now, if we assume, we take into account the errors in the CSI at the receiver or the errors that can happen with successive interference cancellation, this is your signal after cancellation. So you have my signal of user 1 plus any errors from SIC plus noise, right? If these SIC errors are 0, if I do everything perfectly, I have single user performance, of course. And that's typically the assumption as far as I've seen with NOMA and RSMA. In the practical cases, you will have some errors here, and these will contribute destructively to your SNR function here. Then for user 2, it's in the presence of interference of user 1, and this is the classical NOMA SNR for user 2, this user pairing. Now for constructive multiple access, we call it COMA. As I said, the user 1 signal, if I make sure, the aim is to make sure that the signal of user 2 is constructive to the detection of user 1. And that means the interference from user 2 will push the signal of user 1 into the constructive regions. And in that sense, I won't need to decode, I won't need to cancel this interference. It just contributes constructively, right? In which case, I don't need to apply this operation, no need to estimate that signal, no need to equalize or reconstruct the interference and subtract. None of that is required. So that means I have lower complexity compared to this approach. No need for overheads for training and CSI collection. No effects of errors in the CSI, quantization or noise errors, right? Now let's look at the rates, because there's a gain here as well. So here are the rates assuming perfect SIC, which is the typical case in the literature. So user 1 will see single user performance if I have perfect cancellation. User 2 will have to provide a rate that is equal to the minimum of the rate for decoding of user 2 signals between user 1 and user 2. So the minimum between these two users, both users will need to estimate the signal of user 2, right? So the transmission rate that the base station can transmit is the minimum rate of these two rates. And that's actually less than space division multiple access. Now, what you can achieve with this COMA approach is, as I said, user 2 will now contribute constructively to the signal of user 1. And I hope this becomes clear in the next few slides where I explain. So actually, I have better than single user performance. It's not just the energy from my own signal, but the energy from the interference signal, which is now constructive. So I get better performance, better rate for user 1. And here I have for user 2, there's no need for cancellation at user 1. So I can just transmit the user 2 signal with a rate that this user can support. And that's like SDMA, so, space division multiple access. So how does this work? How do I design my signal? So first I need to find a way to characterize constructive interference and to incorporate that design in my precoder. So, and again, we, this characterization comes from the literature, and you can check these papers. So if I look again at the example of QPSK, so here are the 4 constellation points. Here are the constructive areas, the green areas. If I equalize all of them with the phase of the symbol of interest, they all fold onto the real axis, right? So all these constellation points will fold onto this point. And all these green areas will fold onto this green shaded area. This is when I'm equalizing everything with the phase, so the complex conjugate of the symbols of interest. Then looking at basic geometry here, all I need to do is make sure that the received signal, which includes the interference of any other user, falls in the constructive region of the constellation. And I designed that by means of precoding. Then if you look at the real part and imaginary part, and you see look at some basic trigonometry, first thing is the real part has to be greater than a threshold, gamma. And once you have the real part, the imaginary part needs to be within these margins over here. And that will make sure that my received signal, this guy over here, will be in the green area, in the constructive region. That means it will contribute constructively. I won't need to cancel it, and so on. So these 2 constraints are these guys over here. So AR is the real part of the phase rotated received signal, ignoring noise. We're just focusing on interference, multi-user interference. AI is the imaginary part of the same signal. And if you look at the geometry, this triangle over here, you'll get this constraint. As I said, AI is the imaginary, AR is the real part of essentially the received signal equalized by the phase. And gamma here is this distance over here. And you can probably tell intuitively that this is an SNR coefficient, right? It's an SNR quantity. So the greater the gamma, the further away from the decision thresholds, so that essentially the higher the SNR I can achieve. The smaller the gamma, the closer to the decision thresholds, so the lower the SNR I achieve. So importantly, this constraint includes an SNR parameter. And again, if you look closely at these 2, this constraint already includes this constraint. So this is actually the only constraint I need to have here. And theta, I forgot to mention, relates to the order, the modulation order, right? So QPSK will have 90 degrees here, 8PSK will have 45, and so on. So theta is a function of M, and M is the modulation order. And if you do the math, it turns out gamma is directly related to the SNR threshold that I can use in my optimization. And with this kind of formulation, I can go into any classical precoding problem that has an SNR constraint and replace that SNR constraint that treats interference as harmful with this constructive interference constraint where gamma is my SNR parameter. And this is what we did for this NOMA case. So we're designing a precoder to for this scenario of user pairing with NOMA. And here we have for the SNR of user 1, which benefits from constructive interference, we have this formulation. For the SNR of user 2, we have the classical NOMA formulation. So here we have a power minimization. So this is the power, and this is another benefit here. This is actually the instantaneous power of the base station. So in contrast to classical optimization problems where we have, the W, the power in W that's being optimized, remember, a W will be multiplied by the signal, right? The information signal. And that means, in a power constraint where I have a power budget, that means on an instantaneous basis, I may be violating this power budget when I'm multiplying with the instantaneous data, because I'm only constraining the power in the precoder, not in the data symbol. The data symbol will have an average power constraint, an average power of 1, let's say, but on an instantaneous basis, I may be violating the power constraints. Here, this is an instantaneous power optimization. So I'm optimizing exactly the transmit power that goes out of the antennas here. And here I have, this is now the constructive interference constraint. Here's the imaginary part of the phase rotated signal, the imaginary part that I had here, the real part, and the SNR. And I've translated this expression so that I have a rate constraint here. Sorry, no, this is an SNR threshold. We've used R here, but it's actually an SNR threshold. And the same goes for this one, where based on this expression, we have a typical SNR constraint for user 2. So that's user 1, that's user 2. So some results here, a few representative ones. First, on the transmit power. So it's not just the complexity that we're benefiting by removing SIC. We're actually, by exploiting constructive interference, we're benefiting in terms of the transmit power we need to use. So here we're guaranteeing an SNR and we're minimizing transmit power. So we have the performance of orthogonal multiple access, is this line here. NOMA will give you benefits, and COMA will even further reduce the transmit power. And this is with respect to number of transmit antennas. Obviously, the more symmetric the channel, so the fewer the antennas, the more challenging the precoding, the more benefits from constructive interference. And the same goes for the symbol error rate. So symbol error rate for given power budgets. Again, orthogonal multiple access, NOMA, and the benefits from constructive interference in the COMA approach. So, COMA here is a twofold benefit. First, it exploits constructive interference. So it harvests useful signal power from the interference, and that improves, reduces the transmit power for a given SNR threshold, or reduces the symbol error rate for a given power budget. And the second, and probably the ones we were after, was reducing complexity. I'm only going to talk about complexity here, but as I explained, the key benefits are also in circumventing estimation of CSI at the receiver, the errors that come with it, and the quantization. I mentioned this already a few times. But here I'm focusing on the complexity and actually only the decoding complexity. So I'm not taking into account the number of flops that I need for channel estimation or anything like that. It's just about the decoding. Again, it was Abdel here who did these calculations for the complexity analytically. So first thing is, so I need to decode at user 1, I need to decode both signals of user 1 and user 2. And here we're assuming maximum likelihood, but this can apply to other detectors. And I also need to apply detection for user 2 signal at user 2, right? So there's 3 of those in this one over here. And also I need to account for the operation of recreating and subtracting the interference from user 2 to user 1. And that will give you the decoding only complexity of classical NOMA. And a similar thing applies for RSMA. And this is the complexity that we have for COMA, the constructive multiple access, where user 2 doesn't need to cancel anything. It just applies detection. It could be maximum likelihood detection. And user 1 applies constructive interference detection. So it doesn't need any maximum likelihood or anything like that. It always benefits from interference. So user 2 applies maximum likelihood detection in the presence of user 1 interference, right? User 1 benefits from user 2 interference, so it applies a much lower complexity detection, basically a demodulation. And this is in terms of actual numbers. So here we have complexity in numbers of flops with increasing numbers of antennas, and you have NOMA and COMA, and you see about, I don't know, it's about maybe 1/3 of the complexity, and it's only the decoding complexity. And here's the complexity with increasing modulation order. Again, perhaps again a 30% complexity for COMA versus NOMA. But as I said, it's important not to forget that on top of this complexity, we're circumventing CSI estimation and all the errors that come with it. So that was it in terms of dealing with successive interference cancellation and all its overheads and errors. And the final thing I want to talk about is RSMA in this emerging application, a more recent work we did. applying this to integrated sensing and communications. So first, let me briefly outline what ISAC is about. So ISAC is about designing signals and systems that can do both communications and radar sensing at the same time. And this line of research has started basically from the spectrum coexistence scenarios around 2010 between radar and communications. So as classical or traditional radar frequencies were opened up for commercial communication networks, traditionally in the low gigahertz bands where the big radars live, these kind of long-range surveillance or air traffic control radars, these were opened up for LTE and 5G new radio. But more recently, in the millimeter wave bands where smaller types of radars, more down-to-earth radars like the automotive radar or imaging radars operate. And these are now frequencies that are being opened up for 5G and beyond. And this coexistence is problematic. It's messy. You need to deal with interference from the communication transmitter to the radar when it's receiving its echoes and interfering with the detection. And with the radar, and typically traditional radars have very high power budgets, causing a lot of interference to the detection of signals at the user. So you need to manage this interference. You need to coordinate resources, perhaps exchange signaling to coordinate. And this is risky, and this is very messy in many scenarios. And we've seen real problems. For example, I guess you remember the beginning of this year where in the US, planes were halted because of interference from 5G into their navigation system. So this exact coexistence. So ISAC or DFRC, dual functional radar communications, involves this step change from this competitive coexistence into the co-design and the cooperation of the two systems. So the way I will discuss about ISAC is through dual functional radar communications. So that involves one bit of hardware or transmitter transmitting one signal that can do both things at the same time. So it can convey information to the communication users, while at the same time it has all these good properties that allow it to detect targets at the distance. So one signal transmission, one spectrum use, one device, one power consumer, and ultimately a common infrastructure. So it has a few key gains. Perhaps the obvious one is the hardware gain. So where before I had an access point and a separate radar, now instead of two devices, I have this one device that does both things at the same time. And that also means I have one power consumer. So I'm reducing the power consumption and complexity. The second is the spectrum gain, where before I had different uses of spectrum for radar and communications, and I had to coordinate and share with all kinds of other applications. Now I have one transmission doing both, so one bit of spectrum, and this makes space for all the other applications that want to use the spectrum. A bit less obvious gains are now, since you're now co-designing radar and communications from a single transmission, you have the opportunity to design scalable trade-offs between them. So moving on from full radar performance in radar critical applications to full communications performance and anywhere in between. And I'll show you some trade-offs in my results. And also, importantly, beyond trading off performance, you can actually have synergies between sensing and communications. A classical example is having the direction finding of sensing assist beamforming and beam steering for communications, but there are many others in the literature that I won't have time to cover. And also synergies with other functionalities of the network like security and a few others. Now, just to introduce, the design we did here. So here's a MIMO radar only design of a waveform. So we're going to be doing waveform or signaling design more accurately. So here we have a MIMO radar only. So this is MIMO radar. And this is a radar that wants to point a beam to an area of interest where you have a target, right? So ignore these lines here. Sorry, that was for a DFRC system. So here we're focusing on pointing a beam to a target. So there's many ways you can design the beam pattern and the waveform in the space domain. And I have two examples here. So the first one is designing the beam pattern directly. So the power density at every direction. And here you have what you want to design is essentially the covariance of the radar transmit signal, this guy R1 here. And you want to design it so that the power density at every direction, these are the steering vectors of the channel, assuming line of sight, as is typical for radar. So this is the power density that needs to approximate a power density that is the desired power density, right? At the same time, you'll have a power budget, right, for these antennas. And you have these other constraints that have to do with the fact that this has to be a covariance matrix. So one strategy is to approximate, so to minimize the distance from an ideal beam pattern. Another one is to actually design the beam pattern directly. And here this is a 3dB beam pattern. So if I, let's say, want to point my beam at angle θ0, and I want to design the width of my beam to the 3dB width between θ1 and θ2, I can design this optimization. Again, I'm optimizing the covariance matrix. This will be the peak to side lobe ratio, so the ratio between the peak power and all the side lobes. So θm will be the different peaks of the side lobes. θ0 is the angle of interest, and here this is the 3dB beam width. So this is the 3dB factor of 2. θ0 is the center of the beam, and θ1 and θ2 are the 3dB widths. Again, I'll have a power constraint and the same constraints for the covariance matrix. So these are how you can design a radar-only beam pattern. Now, what we're interested in doing here is designing a dual functional MIMO transmission. And we're also interested in a hardware efficient approach where we have a transmitter that, first of all, employs DACs, digital analog converters, with finite resolution, so few bit DACs. And this is a very popular research in the communication only literature. And we also employ antenna selection to also reduce the number of RF chains that we're going to be using. So a hardware efficient approach. Why do we want to employ RSMA here? Because first of all, it's better at dealing with the hardware impairments and the interference that these cause. And secondly, because it has these extra degrees of freedom, this flexibility in how it deals with interference. And you'll see in the results that it gives us better trade-offs between communications and radar performance, as opposed to classical pre-coding. So here's the scenario, again, a bit of math. So a base station that with one transmission, and we're trying to design the signal, the pre-coding here, essentially the signal X that comes out of the antennas, so that we convey the data symbols to the users, and also we have a given beam pattern for the target. So we want to point a beam to our target at the same time. We assume D2A quantization here, and this is a typical approximation used in the literature. So X is the signal I'm feeding into to the DAC, so the baseband signal, pre-coded signal. And this delta matrix is going to be a function of the number of bits that I have in my D2A, the resolution. Then the RSMA signal is a common signal and the private signal pre-coded with pre-coding matrix. And lambda here is a diagonal matrix that models antenna selection. So the actual signal I transmit is the quantized version of that. So employing this model, I have this transmit signal. Then the received signal is going to go through the channel. Now the signal covariance, the transmit signal, the covariance of my transmit signal is this expression over here. And that's important for the radar beam pattern design, as we saw in the previous slide. And that's a function of the pre-coding, of the antenna selection, and of the number of bits in the D2A converter. Now, as our performance metric, we use the energy efficiency because it has a nice, graceful, it gracefully takes into account the rate that we can achieve, the sum rate we can achieve with rate splitting, but also the hardware reduction in terms of the power consumption. So this is the rate, the RSMA rate. This is the total power, where we have the power per antenna, per power amplifier, scaled by the number of active antennas, the power in the RF chains excluding the D2A to converters. This is the D2A converter power. and a few other fixed components like the baseband and so on. And now what we're doing here is we want to design our precoder, our antenna selection, and essentially the common signal rate, so that first of all, we maximize the energy efficiency, the metric we showed earlier, and then subject to the common signals satisfying a rate that makes it decodable from every user, RSMA user. Then this is the radar metric here. It's the proximity. If U is a beam pattern that I designed for radar only application in one of the two, let's say, examples that I showed earlier, here we minimize the distance of what I actually transmit from that ideal covariance of the ideal radar beam pattern. And we want that to be less than a threshold. And by tuning this threshold, you get a flexible trade-off between the energy efficiency in terms of communications and the radar performance. On top of that, we have a threshold for the sum rate, explicit threshold for the sum rate as opposed to energy efficiency, and total power constraint, taking into account this detailed power modeling. And this can be solved with known techniques like alternating optimization, and we did that in this paper. So only a couple of representative results that show the usefulness here of RSMA. So here we have a system with 8 transmit antennas, 2 users, and 1 target that I want to point my beam to. And these results are for 4 bits D2A resolution. And we have other results in the paper itself. So the trade-off here is the energy efficiency for communications. Remember the energy efficiency, I had the communication rate. So this is the communication energy efficiency versus a radar metric. And that's the beautiful thing about ISAC systems, that you can trade off directly communications performance with radar performance. So here we have the case for target detection, where we're interested in the detection probability. So EE versus detection probability of the radar. Here we have the target estimation, where we have energy efficiency, communication energy efficiency against the angle estimation for the target using CRLB. This is a typical metric, the Kramer-Rao or bound, typical radar metric. From all these lines here, I'll probably focus on these 2 trade-off lines. So here's what you have for SDMA, so classical precoding without rate splitting. And this is what you get with rate splitting. And you can see how the extra degrees of freedom shift the threshold to better energy efficiency and better detection. And you can also see the trade-off. This is a typical ISAC trade-off, where you can directly trade off. Let's say if I put my priority on the radar performance, I get my optimum radar performance, the detection, with a sacrifice in the energy efficiency. If I put all my priority in the energy efficiency, I have a sacrifice in terms of probability of detection. And the nice thing about RSMA is that due to the increased degrees of freedom, I have this improvement in the trade-off. I think somebody has forgotten to mute, but I'll carry on anyway. And then it's the same with target estimation. Now we have the energy efficiency with the estimation error. And you can see as I prioritize energy efficiency, the higher values of energy efficiency will give me a higher estimation error. If I prioritize having an accurate estimation, that will have a sacrifice in my energy efficiency. And this is RSMA, space division multiple axis. And this is rate splitting multiple axis. Again, the same shift in terms of a better trade-off between radar performance and communications performance. I think this brings me to the end of my talk. So I wanted to summarize a few key observations and some topics for future work. So in terms of security, I hope I convinced you that there's some interesting and important trade-offs in terms of security in RSMA. So on one hand side, you want to put a lot of signal in the common signal to improve the rate splitting rate. On the other hand, you want to minimize this common signal for security reasons. So it's a very interesting trade-off. How do you design your rate splitting multiple axis, taking into account security? And a lot of the literature does not really consider security for RSMA. And I think there's plenty more to be done in terms of, as I did for the second bit of work, in looking at hardware imperfections and how these affect security and how these affect the design of RSMA and the trade-off between security and rate improvements, or the effects of successive interference cancellation, as I talked about in the NOMA work, and many other open problems. So we just scratched the surface here with a very simple scenario. The other thing is, again, I mean, an observation of my own from the literature is typically the successive interference cancellation at the receiver and the need for perfect CSI is typically overlooked in RSMA works. So I think it would be interesting to see what are the actual real benefits of RSMA if I take into account imperfect SIC. Is it really worth it? I'm sure it's worth it in many scenarios, but what are the benefits I can get from RSMA? And also coming up with these kind of techniques to circumvent SIC and make it more practical in real scenarios. And I think I showed you an example for NOMA. We have one initial example for an RSMA approach, but there could be many for all the different variations of RSMA, the multi-layered RSMA, where successive interference cancellation is more and more of a challenge. And another area I think that's wide open that I didn't get the chance to talk about is a lot of the RSMA stuff assumes Gaussian signaling, as does a lot of the precoding literature. So it would be interesting to see the performance and the design of RSMA once you start looking into finite constellations. So how to do this split. Before I end, for those of you who are interested in any of the stuff I presented, these are the references for the security issues in RSMA. Some references for this constructive multiple access, so COMA, and also our work on constructive rate splitting in the papers over here, and our works on applying RSMA on ISAC. These are the publications I used for this presentation. If you're interested to learn more about constructive interference, there's a few initial works, early works. I would recommend you to have a look at these overviews, which gather the most recent advances. Some optimization-based designs, which can be adapted to include RSMA, and some recent closed-form precoding designs, which make this constructive interference a lot more practical and a lot less complex. And if you're interested in looking at ISAC, so integrated sensing and communications, again, I have here some overviews. There's a book chapter that we're working on that will come early first half of next year. Some, again, precoding optimization designs for DFRC, and some recent experiments that actually prove that this actually works over the air. With that, I'll end here, and I'd like to acknowledge the funding that made this happen, and also my colleagues that we work together on these topics. So let me see if I can unshare my screen so I can see what's going on.
Right. Thank you for your talk, Professor Masouros. So I think during your talk, audience leave some several questions. So I'll read the first question from Sunda. That is SIC easier if both TX and RX have the same imperfect CSI? Can you answer?
Yeah, I mean, I'm not sure which case would be the easiest, but I think my point here was, typically in RSMA, RSMA was designed to take care of imperfect CSIC at the transmitter, right? That was the motivation behind it. So we needed this flexible way of dealing with interference to deal with imperfect CSI at the transmitter. But most of the stuff I see ignore what happens at the receiver. They say, okay, if I achieve a certain rate, I assume that the receiver will detect and cancel and everything. So my message here is that we need to start considering CSI at the receiver and the imperfections of successive interference cancellation, because I think this will, reveal new limits and new regimes for the benefits of rate splitting multiple access. And there's plenty of scope in designing techniques like the one I presented to circumvent successive interference cancellation.
Yeah, exactly. With the imperfect CSI, the receiver, then some error propagation may occur. So yeah,
Absolutely.
yeah.
And you can no longer say, I have single user performance,
Mhm.
or, I can, so that, it's a kind of a stretched assumption, let's
Yeah,
say.
sure. Yeah. And next question is what also I think I'm also curious about this. So what happened in the constellation like a 256 QAM, so very high oscillation where some symbols are surrounded in all direction by other symbols, in which direction can interference push the receive symbol?
Yeah, that's a very good question. I didn't mention that in the presentation, but we have looked at QAM in the literature. There's quite a few works now on QAM for constructive interference. So we haven't looked at 256, these very high constellations. We looked at 16 and 64. Now, what happens? Let's take 16 QAM as a simple example. You can imagine all the outer constellation points, they can benefit from constructive interference, right? I can expand everything.
Yeah.
Then once you expand all these outer constellation points, that makes room for the inner constellation points also to expand and also to benefit from constructive interference. So in this way, we've shown ourselves and others who are working on symbol level precoding that you can actually benefit from constructive interference in QAM constellations as well. As I said, we haven't gone as high as 256, but we have results for 16, 64 that shows similar kinds of gains as with PSK.
I see. So I think better than like 250, like a very the higher order modulation with a different the several multitude, like 8 APSK or that with a smaller number of different the levels of the amplitude would be better for applying the
As I said, I mean, we've seen significant gains for higher order, so 64 QAM, let's say. But yeah, one thing that I forgot to say, constructive interference is more beneficial and more desired when you have a lot of interference, right? So when you have a lot of interference, you typically have low signal to interference plus noise ratios, in which case you will typically not use 256 QAM. You will use lower order modulation. And those are the scenarios where, this constructive interference is most useful.
Okay. So I think that regarding comma, so how does the comma work with more than 2 users? So that would be the third.
That's a good question. We haven't looked at that, but I think it's not very difficult to extend what we did for the 2 users to the 3, 4, and so on. It's not necessarily it's not pairing. You can have groups of users in this NOMA grouping. There, the challenge it would be more for NOMA because you have to have multi-layer successive interference cancellation. So the kth user needs to cancel k-1 users, if I'm not mistaken. So it's a lot more complexity, k-1 channels to estimate, a lot of errors to suffer from. And I think, extending this to more than 2 users is interesting. Yeah. And you can design precoders if you have sufficient degrees of freedom. You can design your precoders so that all these signals are constructive to your signal.
Okay. So so we have some question from the concept of the common message. So why it is named common, why we are concerning the security issue. Yeah.
What was that again? So how does the common message?
Yeah. So what is a common message, and then why we have the common message, why we are concerning about the security issue? Yeah.
Yeah, I could see Mishra replied to this. So, I mean, this is a typical, RSMA structure. So you split the signal into common and private, and splitting the signal into common gives you a flexible, let's say, way of dealing with interference, not as noise, but actually decoding and then canceling it. And that's so common signal exists in RSMA, right? So taking that as a given, we wanted to see the effect of that on security. We worked on all these trade-offs that I talked about.
Yeah.
In security and great gains.
Yeah, exactly. Yeah, just as you mentioned, the trade-off between the performance gain and the security issue. So as Anup shared the so best
Professor Shin,
yeah.
we take this last question because we are already ahead of time. So from
Okay.
Lena, we have the last question, and after that we conclude the session. Would that be okay?
Okay.
Yeah.
So last one is also regarding the construction interference. Does the base station require imperfect CSI to guarantee that the received signal of each user is in the construction region? Is the proposed scheme more sensitive to the CSIT imperfection than conventional scheme?
So we've done studies not for rate splitting, but for classical precoding on the imperfections of CSIT. And no, the answer was no to your question in that domain. So we've seen that the effects of CSI errors for constructive interference, so the losses in performance, were similar to SDMA kind of precoding. We haven't done this study for RSMA, and it would be interesting to look at.
Mm-hmm.
And perhaps there's something more because RSMA is good at dealing with CSIT imperfections. Maybe there's some extra gains there by combining these two.
Thank you for your answer. So I think we are already behind the schedule. So let's thank speaker again here. And so if you have any question, you can send email to Professor Masouros. Yeah. All right. Thank you for everyone. And let's see, 2 weeks later, we'll have another webinar series. So yeah, thank you all.
Yeah, please.
Thank you,
Thanks, everyone.
Christos. Thank you, everyone.
Thank you.
Everyone.
We'll make the recordings available. As you know.
On the
Great. I'll share the
website,
slides as well if you're interested.
Okay.
In the
Thank you.
chat box, I have shared the link of the webinar website. Please visit there to look at the slides and the video. Thank you. Thank you, Professor Christos.
Thank you guys for
Bye-bye.
inviting. Bye.